having calculated the generating functional for the connected graphs, let us now define the effective action in the Euclidean theories. So show Euclidean effective action is given by gamma phi CL equals minus h bar zj plus h bar j phi CL. To do this, you just recall the prescription for action, that gamma bar of phi CL bar, which is the Euclidean effective action, should be minus I times gamma phi CL with Euclideanization. Okay, this is what you use to get to this form. Of course, this is with the original notation. This with bars, we have removed after calculating this, after finding the relation of what should be the right Legendre transformation in this Euclidean case. Following this prescription, we removed the bars and written it in, and remove the bars from our notation. Then from this, it follows that phi CL is given by del Zj del j, and number 2, j is equal to 1 over h bar del gamma phi CL del phi CL. Okay. Now, what would be the steps for calculating gamma? So what one should do is that, so let me refer to this at STP. So first, one uses this equation. One first calculates the generating functional z of j. Once that is calculated, you take the derivative and calculate phi CL as a functional of j. So use 1 to calculate phi CL as a function of j. Then number 2, invert that functional to write j as a functional of phi CL. Okay. And then third step is that substitute this this functional in this equation. Then you basically get the first derivative of gamma as a given in terms of phi CL, so that and integrate it. So it's a first order differential equation, functional differential equation, which you need to integrate. Substitute in 2 and integrate. Now, so far, this is where we stand, but however, there is a problem. The problem is the following. We pretended to write z of j in a semi-classical expansion, which is here. The leading term is 1 over h, then the order 1 term, and then higher order in h terms. That is how we saw in non-relativistic quantum mechanics as well. We followed the same process to get the semi-classical h bar expansion, but this is actually not true as it stands, because we calculate this phi lower bar as a functional of j. So s depends on phi lower bar depends on j also. So there is a j dependence of s implicitly through phi lower bar, and then there is an explicit dependence on j. So now if we look at the dependence on J, it involves a factor of H bar. So here in this action, there is an explicit appearance of J, which involves a factor of H bar. And when you calculate a phi lower bar, so this we have to calculate phi, for phi equal to phi lower bar, and phi lower bar is a solution of this, and that is a functional of J, but each time J appears, a factor of H bar also appears. So phi lower bar J, if phi lower bar itself is an expansion is in H bar, and therefore the explicit H bar dependence that we see here is not the right H bar dependence of this equation, because there is an H bar dependence because the solution and the action is contaminated with an H bar dependence through each factor of J. So that's a problem. So this is basically an illusion that we have a H bar expansion. That is not true. This is, I mean, there is an H bar expansion, but that is not according to the way H bar is explicitly appearing here. The same thing is true for the second term as well. There is a phi lower bar dependence, and phi lower bar is a, so classical solution depends on H bar, and that's what the problem is. And the reason is nothing but the definition of S phi J, where we have put in factor of H bar, because we wanted to get the, we wanted, to facilitate the definition of the Green's function, we wanted to take a derivative with respect to J and bring down factors of phi. That is how the Green's function are obtained. But if we do not have this one over this H bar factor, then this J times phi will be multiplied by this 1 over H bar factor, and each time there's a J derivative of the generating functional, instead of bringing down phi, we will be bringing down phi by H bar. To cancel that H bar, we have to we just add multiplied it by H bar. We could have removed this H bar and found a different prescription for calculating Green's function. Instead of taking derivative with respect to J, we take derivative with respect to J by H bar. Then Green's functions will have only, then we will be bringing down only phi factors. So that's a matter of convention or definition. But this is creating a trouble here for doing this semi-classical expansion. So what we should do is to absorb this H bar into J and redefine it to be J prime. This is the only place where J appears initially. So if we do this, then everything and write everything in terms of J prime, then this contamination is removed, and then this semi-classical expansion is real. So let's do that now. So the point is that the explicit H bar dependence in equation Z is not real as the classical solution phi lower bar J is contaminated with H bar dependence. Given the classical equation CL, and this is only an artifact of definition of S phi J. To make equation Z a valid semi-classical expansion, we should work with the rescaled source J prime is same as H bar times J. Then with in terms of this rescaled source, our generating functional looks the following. Now, when I write this equation, I'm using this notation, same notation Z. Instead of Z of J, we are writing Z of J prime. That's an abuse of notation. Should have written J prime over H bar as functional argument. Here we have done that abuse here, here, and here, but we are doing the abuse for the sake of notational simplicity. I'm clarifying what I mean by when I write a Z of J prime. It is a Z of J, but J replaced by J prime over H. Now let us implement those steps. That I described in the on the left hand side here, 1, 2, and 3. Let us implement these steps for the in the current case to calculate it. The first step is to use this equation 1 here, but now equation 1 has to be written in terms of J prime, and therefore the modified version of that equation will be phi CL is equal to H bar del Z J prime del J prime, because J has been replaced by J by H bar. So we have a factor of H bar in front. And given this, the result that we got earlier about Z, which we have written here, right? So we have to take this. So with a -1 over H bar factor, that extra H bar factor that we have this in the modified equation cancels this 1 over H bar factor. So basically del J prime derivative of this entire quantity with a overall minus factor. That's the result. And let me write that. So in the first step, you have minus del J prime of S phi lower bar J prime, and then minus H bar by 2 del J prime of trace log O phi lower bar of J prime. These are the two terms, and of course this is at order 1 and this is at order H bar. So let us focus on this term first, order 1 term. You see this entire thing is a functional of J prime, right? And we can write, let us write this J prime back in terms of phi lower bar, which is basically the inverse of this. So phi lower bar is a functional of J prime, and its inverse is J prime as a functional of lower bar. We can actually have it written down here more explicitly. So classical solution is given by phi lower bar is actually a functional of J prime, where the equation is that minus del squared phi lower bar plus m squared phi lower bar plus v prime phi lower bar is J prime. So if you view it from the point of view of phi lower bar, then this equation has to be solved. And as I mentioned, one can solve it using the Green's function method, and one ends up getting a power series in J prime. And that solution is basically this, what one refers to by writing phi lower bar as a function of J prime. Now, what is the inverse? The inverse is J prime written as a functional of phi lower bar. And in this particular case, this is precisely that inverted relation. And you can, this equation from the point of view of J prime, the same equation can be interpreted as this being the functional of phi lower bar, which is basically in this case a function, a local function. It's not a functional, it's a local function. In general, if you invert a functional, you get a functional. But in this case, something special happens, that you get it's a functional, but when you invert it, J prime as a function of phi lower bar, you get a function, not a functional. Okay, so that is what we are dealing with. So here, what I'm doing here is that this entire term, order one term, is a functional of J prime. If we know that functional, then the process is straightforward. As a matter of principle, it's a straightforward principle. You know what the action is as a functional of phi prime and J prime. This is the explicit dependence, linear dependence on J prime. And this phi lower bar so there is an implicit dependence of J prime through phi lower bar, which is the solution to this equation. And then once you solve this equation and plug it back in here in the action, you get a functional of J prime, and take a derivative, you end up getting another functional of J prime. Now, once we get that functional, what I would now do is to write J prime as a functional of phi by using this equation. Basically replace J prime by this equation of motion, by the left hand side of this equation. Okay, so that would be writing J prime in terms of phi lower bar. Then my claim is that the final result here is going to be phi lower bar. This is the claim. Now, why do I say that would be the final result? Here is the reasoning. So let us consider this term up, removing the minus, this derivative. So this is the reasoning. So basically, we are taking a derivative with respect to J prime of a quantity which has both implicit and explicit dependence. So what is the contribution to the derivative from the implicit dependence? That will be by using the chain rule del phi of S phi J prime del phi del J prime calculated at phi lower bar. It's a functional chain rule, so I have an integration over the location of phi. Okay, so this is a new notation I'm introducing. This phi, this derivative, is with respect to phi, which is a local dependence. So phi of x, I should have the same phi of x. Okay, so this is let us start with this. This is not a local quantity. This is just a number. But when you take a derivative, I'm taking a derivative with respect to a local field J prime of x. So this quantity depends locally on x, that x is sitting here in this expression, and this one is coming, this phi is coming from the, because of the chain rule, and this phi is also a local field, so let me call it y, then it will be y, and I have to integrate over y. So but I'm not writing this y is x is here, I'm writing only phi. It means integration over the location of phi. That's what it means. Then the derivative, the contribution to the derivative from the explicit dependence on j prime, which is del j prime of s phi j prime calculated at phi lower bar. Now this quantity, is same as del s del phi calculated at phi lower bar and del phi lower bar del j prime with the integration of phi location, and but this is 0 because of the classical equation of motion. So this part is 0, and this part we know that the explicit dependence of the of action on j prime is minus phi times j prime. So this is equal to minus phi, and therefore minus phi lower bar. Okay, and multiplied with this additional minus sign, it is phi lower bar. That is how the reasoning goes. Okay. So the result of this analysis implies result of the analysis is the following. That phi CL, which is the functional of j prime, is given by phi lower bar functional of j prime plus an order h bar correction, because I haven't taken into account this part. That is the result. And then according to so basically in the first step we said here that use 1 to calculate the functional phi CLJ, and that would involve actually finding in, if you follow this algorithmically, then and that would involve finding phi lower bar of j perturbatively in power series in j prime, substitute that into action, then get action entirely in terms of j prime, then take derivative with respect to j prime. This is a very difficult calculation, long calculation, solving it in Green's function method, perturbatively putting that. But this argument, and when you do that, when you do calculate the, when you take this derivative and get this psi of j prime, then replace j prime by this equation, you are supposed to get back phi lower bar. This is the this is what this argument shows. So this is a shortcut trick to get. So let me. So this is an explicit. This is a this argument. This is an indirect trick or argument to compute phi CL of j prime without I mean phi CL, I haven't calculated the dependence on j prime, though I have calculated phi CL in terms of phi lower bar, which will be useful in the next step, as we will see, without explicitly solving equation classical to find, without solving explicitly, this equation. That's it. This is what we have done. But now let's move on to the second step. Second step is inversion of this relation. Writing J prime in terms of phi CL. So J prime in terms of phi CL is J prime phi CL is phi lower bar plus an order H bar term. This is what we have seen, and that is same as J prime at phi lower bar. If you just think of it as Taylor expansion around phi lower bar, Taylor expanding J prime around phi lower bar, then it is this plus an order H bar contribution. But J prime of phi lower bar is nothing but, as I said, this one. So the result is therefore is minus del squared phi lower bar plus m squared phi lower bar plus v prime phi lower bar plus order H bar. Now in this equation, I can easily replace phi lower bar by phi classical, phi CL, because the difference will be order H bar, which I'm neglecting anyway. So this is going to be minus del squared phi CL plus m squared phi CL plus v prime phi CL plus order H bar. And therefore, in the third step, we write down the first order functional differential equation for gamma, and that's given by this. At the leading order in H bar, and we know that it is nothing. This is nothing but the derivative of the classical action, right? I mean, that is the equation of motion. So this thing is nothing but the derivative of the classical action with J equal to 0. So therefore, this gamma is nothing but the classical action. So this is a semi-classical analysis where we see but for arbitrary, but around a class, but around an arbitrary. Okay, so this is a more general. So earlier when we did this, we give the argument that in the previous part we gave an argument here that in the H bar going to 0 limit, gamma phi CL is same as S phi CL, but that was that argument was given by using the Feynman diagram techniques and calculation of the generating function in the perturbation theory, and giving this and arguing this kind of results, right? That shows that for a perturbative expansion around a Lorentz invariant vacuum, this statement is true, but this statement is more generally true around as even in the semi-classical expansion, when you expand the action not around the Lorentz invariant constant vacuum, but around an arbitrary classical solution, this result is true. This is what is being shown here.